Okay, welcome everyone. My name is Robin Burgess, and I am floor up from John at the LSC. I'm also director of the International Growth Center. So this is one of a series of lectures on PhD level environmental economics, and this was set up with Kelsey Jack from UC Santa Barbara. We're going to have 10 lectures on different topics of environmental economics, and today we have a lecture which is going to be by John Van Reenen, who you can see here on the screen, and who's from the LSE and MIT, and Mar Reguant, who is from Northwestern and Barcelona School of Economics. And they're going to be focusing on this very big topic of economics of renewables. And I think what's exciting about this particular lecture is that John is a world expert on innovation and the diffusion of innovations, whereas Mara is sort of coming much more from the IO side of things. So I think what we're going to have today is for John to speak for half an hour, and then to pass to Mara for half an hour. And what I suggest is if you'd like to be a live participant, could you raise your hand in the chat screen, and then you can be elevated to become a panelist. And if you do that, then please keep your camera on so that we can have a sort of a series of faces to look at as we go through the lecture. So I think I'll just now pass this to John. Thanks.
Thanks very much, Robin. And I'm really excited and delighted to be able to talk to you a bit about the economics of renewables, which is, such an important topic. You hear about it all the time in the newspapers and the media. So I've made these slides available online, and there's a reading list that you can also look at. So, I'm going to go at a reasonably quick pace through a lot of material, so don't feel that you need to take it all in. They'll be able to look at it afterwards if you want to look at some of the details. So I'll talk a little bit about facts to begin with. Then I'm going to talk about some of the theory of technological change, of innovation in general, actually, but also as applied to the renewable space, and then talk about some of the empirical work where people have been looking at the determinations of innovation for renewable energy with a kind of policy focus. So first question, what are renewables? Well, the usual definition is it's a form of energy derived from natural sources that are replenished at a higher rate than they are consumed. So things like solar power, wind power, hydro, geothermal, ocean tidal, and bioenergy. And of course, very important for the green transition, because about 73% of global greenhouse gas emissions are attributed to energy. So if we want to think about decarbonization to deal with climate change, then it's very much reliant on electrification and therefore clean energy. So it's going to be absolutely vital if we want to really do something about getting down to net zero and having this green transition. So if you look at the share of renewables, so here's some measures of the growth of electricity production from different sources. You can see you might think as an optimistic picture. So here's kind of solar power. Here's kind of wind power. Here's coal and gas at the top. So very fast increases of the production of electricity from these renewable sources. However, even today, it's still the case that fossil fuels dominate. And notice this is a log scale. So it's still the case that oil, gas, and coal are dominant. So yes, renewables are catching up, but there's still quite a way to go. Why has there been such a big increase? Well, one of the reasons is just the price of renewables has fallen very dramatically. So this is a kind of long run picture since 1880 to today. And on the y-axis here, you have a kind of measure of the cost of different types of energy. So here you can see this very dramatic fall of the price of solar, also wind, and some other renewables. If you compare that to more traditional fossil fuel sources like oil or coal, you can see there is not that, there's certainly not room for cost reductions in the same way there have been for renewables. So coal's an interesting one. So for a while, until the 60s, the price of coal was going down, but since then it's actually been going up. So just focusing on one renewable, solar power, and over the kind of last 40, 50 years or so, this again shows you this kind of fall of the price of solar, again on this kind of log scale. And these lines are pointing out is that the predictions of the fall of the price of solar power have been too pessimistic. So this is what people were predicting the fall of price of solar was in 2000, and this is what the price fall actually was. So the price fall has been much faster than people had been predicting, and I think a lot of that is to do with technological change in the solar industry. One of the factors which is important has been the rise of China. So you can actually see, if you look carefully at the graph here, the price fall has been particularly fast since around about 2007 onwards, and that's coincided with this very rapid rise of China in the production of solar photovoltaics or PV production. So China basically went from 0 market share to about 60% market share within the space of 10 years. So there's been this increase of output, of solar, and a lot of this has actually been driven by what's happening in China. Interestingly, China, and I'll come back to this later, has not only been producing more, but it's also been innovating more as well. So, one measure of innovation, which we'll come back to, is patenting activity. So this is solar patents. And you can see this kind of, explosion of patenting that's happened in China over the course of this period as well. So it's an important thing when we're thinking about renewables to think of, the growth is being partly caused by greater production, but also being caused by this innovation, which has gone along with reduction of costs and helping drive down the price of solar. So how should we think about innovation in the renewable sector? Well, one aspect is the kind of adoption decision. So key decision maker here are electricity generators. When we're building a new power plant, are you going to choose a coal-fired, a dirty power plant, or say a solar or wind, a kind of clean source of energy? That's a key adoption decision. Also, households are making decisions about whether or not you install solar panels on your roof, whether you use heat pumps, and so on. So households also matter, but a big part of this is what's happening with electricity generators. Now, many factors are going to determine this decision, but a key one is going to be the cost of producing energy and the price paid for the energy produced. So both the current price and the expected cost and prices are going to matter. Think of these. Now, these are often, say, for a power plant, large and partly irreversible decisions. So expectations over the future and uncertainty over the future is going to matter a lot. Often governments, for example, will have feed-in tariffs, which guarantees a price for renewable energy. That's going to incentivize the use of more renewable energy. But the more uncertain that the players are, that the people who are building the power stations are, the less likely they are to react. They might choose to wait and see. So this really emphasizes the importance of, when you're making investment decisions, when there's risk aversion or whether there's uncertainty, that you might delay what you're doing depending on how uncertain you are. That's why policy certainty often matters a lot in these type of decisions. So costs matter, including security of supply, prices, demand, policies, and the existing stocks will matter as well. So when we're thinking about power plants, a major issue is often when do I retire the old plants, the coal-fired plants? As for these, the marginal cost is actually pretty low, even though the kind of sunk cost has been pretty big. So say for richer countries, which are often deciding whether to close down some of the plants, the existing stock is going to matter, as well as when you're deciding whether to have another plant. So how should we think about innovation? So what the old traditional view of thinking about technology is that technical change is kind of exogenous. It's like manna from heaven. It's kind of brilliant inventors or government labs which creates these. The modern view from endogenous is a kind of endogenous growth view, which is that innovation depends on firm decisions, and firms will decide whether and how much to invest in research and development. And this research and development goes into eventually reducing the kind of costs of the different products such as renewables. And this will, this responds to incentives, whether those are government policy incentives or changes of the economic environment, demand expectations, the price expectations. And ultimately, it's a sense of, if it was a kind of decentralized, purely, free market economy, how much profit does a firm expect to make from investing in these in research and development? So those of you interested in getting deeper into this, you can peruse my new book with Ufuk Akajit, which actually tries to go through these type of issues. This is often drawn on work by Philippe Aghion and Peter Howitt around the economics of creative destruction. There's in my lecture today, I'm going to draw very much on some of the work in this book, particularly by de la Chapetre and Hummus, who have a very good chapter. Okay, so productivity increases through the innovations, or depend on the innovations diffuse. This can often be slow due to information, low skills, incentives, and so on. I'm going to focus a bit more on the innovation, the kind of how you shift the knowledge frontier for now, but also I'll say a word or two about the diffusion towards the end. Okay, so we're gonna have to have a little bit of algebra to make things. This is a PhD course, so we have to have some Greek algebra in here. I'm going to focus on what's called a directed technical change model. So in innovation models, there is the kind of speed of technology, and there's the direction of technology. So the early endogenous models focused on just the overall rate of growth. And the more recent models, especially when I'm thinking about green versus dirty technology, think about how you allocate your innovation across different types of technologies. So we're going to be thinking of clean versus dirty technologies here. So imagine we have a final good. This is going to be Y. It's produced from two inputs: a clean input, think of that as solar if you like, and a dirty input, think of that as coal. And in order to produce the good, you have to combine these two different sources of energy inputs, partly clean, partly dirty, and you combine these with an elasticity of substitution. So these are going to be substitutable goods to some extent. That's going to be important, as we'll talk about. So that's governed by this kind of epsilon parameter here, which is elasticity of substitution between clean and dirty. So when we think about greenhouse gas emissions, that's going to be a function of the amount of dirty production. So the more dirty production there is, the more coal there is, the more pollution there is. And then if you had a whole integrated assessment model, the pollution would determine the damage that does to the environment, and that would be a feedback loop you would take into account in a more fully specified model. So innovations can reduce the cost of producing either clean or dirty. We're going to abstract, although it's easy, we'll show this in the extensions, to have grey innovations which say reduce the emission intensity of dirty. But for now, we'll keep it simple. Just think about innovations which can reduce the kind of improve the productivity of dirty or improve of clean. And the production of energy in each sector, either clean or dirty, is going to, we're going to call this J. J is going to be either C for clean or D for dirty. And the way that it's going to work in each sector is that we're going to use labor, use people, and we're going to combine that with machines. And the machines are going to be employed in one or the other sector, the clean or dirty sector. Each of these machines costs something, 1 minus beta in this setup. And each of these machines has a level of productivity. So we'll call each machine I, and AJI is the productivity level for that particular machine. So innovation is going to be about reducing the cost of producing these machines. So think about this as solar panels, if you like. The degree to which you can reduce the cost of solar panels is going to be the way that this A term changes over time, the kind of productivity term changes over time. So what we're interested in is how this A term evolves and what determines it. So the way that this is going to be modeled, as in kind of Aghion and Howitt, is it's going to be a quality ladder. So at the beginning of the period, we're going to think about the scientists or R&D workers, and they can work in the clean or dirty sector. So that means for a given number of scientists, the more scientists who work on the clean sector, the fewer are going to work on the dirty sector. So there's a direct crowding out effect, which is going to happen, or vice versa. The more, the more people who are doing innovation, the more scientists are involved in innovation, that increases the probability of innovation by this E to J term. And this then, if you're successful at innovating, you get increased productivity, and we'll call that gamma. If you are a technology leader, you're the kind of the person who's producing the best technology because you've just innovated, then you can charge a monopoly price or a higher price. You've got a patent on your innovation. We'll assume that lasts one period. So we can think about the aggregate technology in any sector as AJ, and that's just going to be the kind of think of this as the sum of all the technologies which are being produced for that particular sector. So there's going to be a law of motion which determines how the technology evolves over time. So my kind of technology, my productivity of a machine today depends on my productivity yesterday, and it depends on how many scientists are involved in working in the clean or dirty R&D sector, the chance of success, and the step size, the improvement of productivity. So that's going to determine how productivity changes over time. So you can see that there's a kind of key externality here. So every time an inventor innovates, they build on the shoulders of giants. So your new innovation builds on the old innovation, and that's a good thing. That's how knowledge progresses. But of course, that is an externality. So once you've increased the technology and your patent runs out, that technology spreads across to other kind of people in the economy. So that benefit is not priced in. It's that knowledge benefits everybody, is not fully internalized, and that will generally mean there's too little R&D investment, because the benefits are much larger, the social benefits are much larger than the benefit that the individual inventor gets. That's the key thing about the knowledge externality. It has this public good aspect to it. So you can solve all this. I'm not going to go through all the details, but you can solve this model. What you end up with is a kind of relatively simple equation, which on the left-hand side, this tells you the profits that you get from putting your efforts innovating into clean technology relative to the profits you get from the dirty technology. And that's going to depend on kind of three key factors. This is completely generic to a lot of the class of directed technical change models. So the key thing is this term at the end. So this is a summary of the relative productivity of clean versus dirty technologies, the kind of state of the art. And the more dirty technologies there are around in the economy, the more likely it is that scientists will carry on innovating in dirty, because you're building on the shoulders of giants. So there's a lot of knowledge of oil and gas, the natural thing is that people carry on working in oil and gas. So that's the sense in which there's kind of path dependency. There's a lot more relatively dirty technologies around relative to clean. There's going to be a lot more innovation going on of dirty relative to clean. So that's one factor. That's an important factor. The second factor is the kind of market size factor. So this is capturing the bigger the market, and in an expectation sense, the bigger the potential market, the more likely you are to invest in it. So you think, if the market's bigger, you're going to make more money from a R&D investment. Therefore, the more likely you are to invest in it. So both of these are kind of bad news for the current. If you think of, if you have a lot of dirty, the market size is very big. A lot of people are currently using dirty technologies. This is going to mean that scientists and R&D tends to be focused on those dirty technologies. There's an offsetting effect, which is this price effect. So because in the initial condition, the state of clean technologies is relatively lower than dirty technologies, the price is relatively higher. And this actually gives some incentives for people to actually go for the less known technology in this case. Now, you can show that in the way I've set the model up in this is drawn from this kind of Aghion Acemoglu Hamas model, that because these are substitutable energy products between clean and dirty, and we've assumed that they're substitutable, that the effect of this direct productivity effect is going to outstrip any price effects. So in this type of model, it's always going to be the case that the path dependency effect is the largest effect that's going to outweigh the price effect. But it will depend on different models. And I'll show you one where that's not the case. So there's three kind of key implications that we get from this kind of model. The first one I've kind of stressed is that if we start off in a situation where dirty technologies are more abundant, they're initially the most advanced sector, then you get this path dependency. So innovation will be directed at the dirty technologies relative to clean technologies, and you get this kind of lock-in effect. The policy implication is the social planner can try and avoid this by actually focusing a lot on policies in the kind of early part of the transition. So either with a carbon tax or with, say, clean R&D subsidies or clean subsidies. The model kind of suggests heavier action at the beginning can help you switch the direction of technology, and then later on you can relax the policy as the amount of stock of clean knowledge builds up. A third implication is that, in fact, often economists say you just need a carbon tax. This type of model suggests you need both a carbon tax and a research subsidy. And the intuition is that in order it's like this, imagine this kind of super tanker is going along, in one direction, which is the dirty kind of direction. If you want to shift the super tanker, doing that through changing demand through a carbon tax will help, but it will be, in the future. Whereas the research subsidy can shift that tanker sooner, and it can actually move it, and you can show that's actually a mix of policies is actually the first best on these type of models. So there's lots of extensions and applications of this. One way there's the nice paper by Reenen and co-authors here calibrates this to the kind of US economy, and indeed suggests that there's having these early action is the kind of best is a good policy to do here. There's another application that Philippe and co-authors have done, which has looked at the shale gas revolution. So you might think the shale gas revolution is a great thing because, gas is cleaner than coal, but they show that in these type of directed technical change models, the problem is that in the short run, the fall of the price of shale reduces emissions as coal is used less. But in the long run, because it incentivizes more research and development to go into fossil fuel, kind of gas plus gas, instead of clean, it actually means that clean innovation falls in the long run. So again, it suggests that the shale boom may have contributed to a slowdown of the rate of clean innovation in recent years, and you need to have some clean R&D subsidies again. Not every model will give you the same thing. So Hassler, Cressell, and Oliverson have a model where, in fact, the elasticity of substitution between energy and other inputs is actually very low. So there's a kind of complementarity between energy and other inputs, and this actually means that the price effect that I showed you dominates. And in their type of model, although you still need a carbon tax to deal with the kind of external climate change, that does most of the heavy lifting for the transition. You don't need these additional clean research subsidies in their kind of setup. So a lot depends on how substitutable we think some of these technologies are. Okay, so just to draw some conclusions from the theory, that I think that the standard model says that directed technical change provides a lot of policy answers that differs from models with exogenous technology. In the case, which I think is the more plausible case of substitutable types of clean versus dirty, especially in the long run, we need to front load a lot of environmental policies to kickstart the kind of green innovation transition. Carbon taxes are also important, but they're not the only thing. They need combined with R&D tax credits. And bridge technologies like shale gas may actually backfire if not accompanied to have efforts by carbon-free technologies. So in the last 8 or 9 minutes, let me talk a little bit about some of the empirical evidence. Some great reviews of this. There's a nice by Grubb et al. or Pop have some good reviews of this. One of the focuses of the literature has been on looking at the impact of energy price changes as a proxy for the carbon tax on innovation. So like the oil price shocks in the 1970s, for example, or tax-adjusted fuel prices. So some of the early work was done by Newell et al. On energy efficiency of home appliances. And they looked at the effect of energy prices and found that when energy prices were higher, there was more technical change in air conditioning. And this was reversed after the 1970s oil price hikes. Pop, and this is quite a well-known AR paper in 2002, looked at patent applications in the US, and then looked at 11 different energy technologies, such as solar panels and fuel cells, and found that when energy prices were high, you saw firms innovating and patenting more in these types of energy technologies like solar power. The short run impact was pretty small, but the long run impact was, not non-trivial, about 0.35. So a 10% change in the price led to about a kind of 3.5% increase of patenting activity, and a lot of this was in the first 5 years. There's been a lot of follow-up work to that from many other countries, which has also, shown similar effects. One of the issues is that these are using kind of macro data. So this is using changes of energy prices across, say, the whole of the US economy, and innovation across the whole of the US economy is measured by patents. The problem with that is there could be many other things happening at the macro level, so you can't include dummy variables for time to identify the effect. So some of the more recent work has tried to use microdata, where you could exploit differences across firms in order to deal with some of the macroeconomic shocks. So some work that I've done with co-authors, and this is in the car industry, we look at the electric cars versus internal combustion engines. We could use tax adjusted fuel prices across different countries, weighted by a firm's exposure to that country. And we found that when the tax adjusted fuel price went up, that stimulated more clean innovation. It's disincentivized dirty innovation, and even increased some kind of energy efficiency, grey energy efficiency. And we found very important kind of path dependency effects, and simulation showed that this path dependency exasperated this gap between clean and dirty knowledge. So people have taken this similar methodology and actually looked at this in electricity production, shown similar things, that innovation in electricity production, as measured by patents, responds to fuel prices. That class of empirical papers is looking at energy prices. Others have tried to look at direct renewable policies. So a few of these papers have tried to look at things like the European emissions trading system. There's discontinuities in how that cap and trade system works, and you can use those regulatory thresholds to get try to get a causal impact using the microdata, again suggesting that the ETS carbon price increased low carbon patenting. Some other people have used in the literature pollution abatement control expenditures, other kinds of energy policies. These are kind of if you're interested in the effect of innovation policies directly, these are kind of indirect type of things. They're kind of saying you're changing the price of energy through a carbon tax, or the kind of market size. There's a much smaller literature, very small literature, looking at the direct effect of innovation policies. I'll mention a couple. The best one I think is by Sabrina Howell. She has a really lovely study of the US Department of Energy's Green Small Business Innovation Research Awards. So these are R&D grants given out to firms, and she managed to get data on all the applications and the scores that were given to the different research proposals. So because of that, she can see the scores, and she can see the cutoff for who got the grant and who didn't get the grant. So she can do what's called a regression discontinuity design, and compare the kind of just winners to the just losers, to try and get the causal impact of these green energy grants on the eventual outcomes, such as patenting, raising money for venture capital, and so on. So she finds positive and quite big effects, especially for financially constrained firms. So if you look at this kind of the award decision, you can see this big jump up in the probability of, say, site-weighted patenting just around this threshold. And you think firms which just won compared to just lost are kind of almost identical in every respect. So this is quite a nice way of trying to look at the causal impact of getting an R&D grant on innovation in the future. I have a paper with Robin and several other co-authors here, where we look at the impact of Chinese industrial policy towards the solar industry. Different cities in China introduced different types of subsidy policies for solar power at different times. So some of these were production subsidies, some were innovation subsidies, some were demand subsidies. We found that supply side subsidies, both production and R&D subsidies, had large effects on solar output, productivity, and innovation. And we argue that some of the mechanism is through learning by doing. There's also some evidence of spillovers as well. So just to show you that in the picture, this is an example of a 2007 policy where you can see a big jump up of patenting activity just when the policy was kind of introduced here in 2007, for example. So a broad conclusion from the empirical literature, I'd say that there is evidence that renewable innovation can be induced from a variety of things like tax-adjusted energy prices, indirectly by renewable policies to increase demand, or directly via renewable R&D subsidies. This last one is probably the where there's least work done. There's been progress on identification, moving from the macro level towards better designs at the micro level. One of the weaknesses is that I think a lot of the innovation measures are on patenting, and that's very useful. It's very observable. You can try and adjust the quality through citations, but many innovations are not patented. They're very heterogeneous. It'd be great to see some more direct measures of energy cost reduction. There's some papers which try to do that through directly looking at efficiency of different products like solar panels. There's less knowledge about spillovers, which is critical for the kind of the knowledge externality. And there's some evidence that these might be larger for clean than dirty, but this is a real area. This could be some more work. And it'd be great to know more about different types of innovation. So learning by doing, radical versus incremental innovation, and so on. So I'm more or less run out of time. I put down a bunch of papers on adoption models and work on adoption, which you can look at if you're interested. But let me just draw some general conclusions before I hand it over to Mar. I think, there has been this remarkable and rapid technological change in renewables, which in many ways are now getting competitive on price with fossil fuels. And that's a source of optimism for thinking about the kind of green transition. Some countries like China have had a very important role in the growth of production for renewables, like in solar power and wind, and this has helped drive down the price. But understanding how we get technological innovation is interesting as it's an important application of direct technical change. It suggests that price effects and market size effects are critical. And there's a suggestion in literature that if there's substitutability between clean and dirty energy, then having very strong early interventions because of this path dependency could be very important. And I think that my broad view is that carbon taxes are really important. They're unlikely to be enough by themselves. You also need to combine them with these innovation policies and other kinds of policies. So I think for the empirical work, there's some calls for optimism. Lots of room for contributions, though. So I hope many of you in the audience will be interested in picking up some of this work in your PhD. Okay, so thanks very much, and I will hand over to Mar.
Awesome, thank you so much, John. You gave such a nice overview, so dense that it will be hard to follow, but I'll try. So let's see. I think you can see it properly. Let's see. Why don't I see it? Hold on a second. Can you share here? No, I couldn't see it highlighted. Now I can see it. Great. So I'll be talking about renewable power, focusing on more hourly data sets that look at renewable power. So John looked at innovation and the bigger picture of how these costs have been going down. I will be looking at the more hourly and daily operation of renewables, some of the challenges that we've had, but also lots of the successes that we are seeing. So I'll basically talk about how to do a cost benefit. And this is abstracting away from innovation, by the way. It would abstract away from any innovation benefit from these policies, but rather, given that we have the renewables, how are they performing? Are they reducing emissions? Are they reducing costs? And again, the two case studies that I'll talk about will give you a positive picture of the impacts of the renewables. So I will not spend too much time here because you probably already know this, but the electricity sector and renewables are at the center of the fight against climate change. because it's the one sector that we know how to decarbonize. And since very recently, now we can do it economically. So this goes only until 2018. If I had even more data, it would drop down. Solar costs have dropped down until 1,000 with only 5 more years of data. So we can see huge reductions in cost with only 5 more years. Onshore wind has maybe not declining so much, and it's also around 1,000 per kilowatt installed. But then we see offshore wind, which has also taken off. And one that's not presented in this picture, I couldn't fit them all in such short slides, it's batteries. Batteries are also seeing great declines in costs. Natural gas is still there cheap in the United States, but not everywhere else. So these renewables are at the moment the cheapest technology in many, many, many countries. And that does not only include Europe, certainly during the crisis, but even Europe during normal times, and definitely many, many countries in Africa or many, many countries in Latin America that are not sitting on top of gas like the United States. So it's great news for the energy transition. It doesn't no longer require you to be a pioneer. It does no longer require you to have to spend lots of subsidies to make this happen. For many, many countries, it's already the cheapest technology available. And on that note, solar is the one that I would highlight as probably the overall cheapest because it's also extremely scalable. So you can do solar for peanuts, or you can do solar in huge scale, and it can be adopted easily at many, many stages of development. For wind farms, these are extremely large installations. They might require much more concentrated industries to deploy them. But for solar, it's kind of the best news that we've had in climate for a while. And if you're following the news, there are not very good news on that front. So it's the one place where we have good news. So there are still a couple challenges with renewables. One that has been of great concern, but it's slowly becoming not concerning, is what we call intermittency. Intermittency is a bit of a vague word to refer to the fact that renewables are a bit uncertain, and also they come up and down. So at night we don't have solar, one day it's windy, another day it's not windy. This is very different from our good old life with fossil fuels, where we can just turn them on and off at our own will. For wind and solar, we are at the mercy of the weather conditions, what time of the day it is. So this used to be quite concerning, and still is a little bit, because it requires us ramping up and down our grid. For times in which we have a lot of wind, we have to ramp things down. When we have less wind at night, we have to figure things out. Electricity is a very reliable source of energy, but it's a high precision source of energy, and we need to make sure all the time things are in sync. So this intermittency, initially for the engineers operating the grid, for the economists working in this area, myself included, we worried a lot about this. So two things have happened. One is innovation, but not on the blades or on the solar panels. There's been a lot of innovation on how to integrate the renewables and reduce the cost of intermittency. There's also been innovation in batteries that is making this intermittency less of a concern, although it's fair to say that innovation is still a work in progress, but it's declining. The cost curve is declining fast. So the other challenge is the transmission grid, and you might hear a lot about this in the news. So we might have solar resources, but there might not be where we need them, or we might have very windy locations where people didn't usually live there. So what we are seeing is that more and more the transmission grid can become a bit of a bottleneck. Although there's been also a lot of innovation there. Some of it is regulatory. States and governments are trying to make it easier to put transmission lines and simplify a little bit, streamline the process. So there could be some political economy innovation there. But there's also been technological innovation in how we transmit power. And for example, the transmission grid back in the day used to be a very fixed dinosaur, and now we can dynamically change the network. And sometimes we can allow power to go through a line, sometimes we can remove that power or reduce that power, something that we couldn't do as flexibly before. So there's a lot of technological innovation that's complementary to the technological innovation that John was talking about, that's making the integration of renewables easier. And it's decreasing a little bit these two challenges. So I'll talk about how to do the cost benefit of renewables when we think about these two challenges. And I'll talk about two methodologies that we have been using as economists. One is regression analysis and one is structural models. And I'll give you a couple examples. It's an ambitious agenda, so I'll go relatively fast, although I don't think I'll mention as many papers as John, so I think you're good. What I wanted to talk about is what we can do as economists to see how much of a problem are these two challenges, how are they affecting the cost benefit of renewables, and then make some take some policy conclusions from there. So when we do this cost benefit analysis, as I was mentioning, usually we will use quite detailed operational data from the grid, because all of these things are basically an hourly problem. For the case of solar intermittency and wind intermittency, obviously because solar and wind conditions change every hour, but transmission, also the flows in the electric grid can also change hour to hour. So we need to have a very granular type of data. With that data, we typically look at the costs and benefits. And here you could put innovation, all of that. There are some studies that John mentioned. I focused on the ones that are not looking at innovation. So when we take a more narrower view, we usually look at what the panels costs or the windmills cost. We look what it costs to the people that are already there. So how much fossil fuel consumption we might save, but also how that's affecting some of the stranded assets that are already there. We can look at the impact of intermittency, and we can also look at the cost of transmission investments. When we think about the benefits, solar and wind have several benefits. One is price reductions. They are very cheap at the margin. The other one is pollution reductions. This would be local pollution. Then greenhouse gas reductions, which is the climate provoking emissions. And then there can be benefits on resilience. I think some of you were asking, are renewables adaptation or mitigation? We tend to think about renewables as mitigation strategies. They try to substitute emissions and try to decrease our carbon footprint. But for many of these technologies, they can also be very resilient because they can be very granularly installed. They can also be used to create what we call islands. So when things don't work at all, we can still maintain parts of the grid operating with solar panels, for example, and batteries. So these are some of the benefits. And then additionally, investment spillovers. Here, again, I should put innovation, but it is a bit of a shorter run type of analysis. So I'll talk about the methodologies. We, as economists, have prioritized two methods. One is regression methods that will use very detailed hourly data to see what happens in days with a lot of wind or days with a lot of solar and days with no solar at all or no wind at all. So this will tell us the short run impact that these technologies are having on the grid, and it will allow us to say how much wind and solar are decreasing emissions. That would be the climate benefit, how much they are decreasing prices, how they are impacting costs. And here it's a bit ambiguous. They could be increasing the cost of intermittency, but they are also decreasing the cost of burning fossil fuels, and so on and so forth. So these papers typically run the models at an hourly or daily basis, and it's usually a very long time series, a year data, 10 years data, but basically many, many hours. For the structural methods, this will require modeling tools that are basically using mathematical programming to build a model of the grid. And then we have a model of the grid, let's say the grid in the UK, that we can run and we can play with it. Typically, the temporal aggregation is also hourly, and we model the detailed operations of the grid at every hour. And we try to see if we can explain how the market works, but also what would happen if we do some fudging with the market, something that would be harder to do with the regression methods. And one example of such counterfactuals would be, okay, imagine I have the UK market, I have modeled it with a lot of detail. What would happen if I put this kind of a subsidy? What would happen if I put this kind of a carbon tax? And we can kind of play around with that detailed model. So I'll show you two examples, one using regression methods, looking at the cost of intermittency, which was challenge 1. And then I'll show you another paper using structural methods to do transmission investments, which was challenge 2. So here I put a bit of a literature review, and I mentioned several papers that are at the frontier of these different things. So these are kind of the first papers that quantify the emissions benefits from producing from wind. This is one quantifying the price effects of solar. This one is looking at the benefits, environmental benefits from transmission in Texas. This is one looking at the overall subsidy policies in Germany and Spain. One for the Nordic market, and so on and so forth. These last papers here are the more kind of, I would say, quant heavy papers, building structural models to look at reliability policies, so how intermittency affects the value of solar, in this case with data from Arizona, and this one looking at the adoption of batteries and how to value battery behavior, how to evaluate battery behavior. It's an incomplete list because it's a large literature, but I leave it here in the slides if you are interested in this trend of the literature. So let's go to the first challenge, intermittency. I'll show you a case study from Spain where we downloaded very detailed data, hourly data from Spain. And the unique thing about this study is that not only we had data on emissions and prices, which is very common, we also had detailed data on things like congestion and reserves and reliability, all the things that need to work out, but that are very like nitty-gritty, very nerdy. So in Spain, all that data are available, and it gave us a nice measure to quantify, is wind power making these things worse? So that was kind of our question as we started. So what's the impact of wind? But again, emphasizing the impact on these operational data, these operational costs that typically people cannot measure, like congestion costs. What we find is that the overall effect of wind is very positive. Consumers were better off. And on top of that, intermittency that doesn't change this finding. So this intermittency did increase a little bit the costs of wind, but it doesn't change the overall conclusion in the cost benefit. The other thing that we find that I should have highlighted here is that even in the days in which there are massive amounts of wind, we don't see lots of operational problems, and we don't see the costs of intermittency blowing up, something that people, again, were concerned about. So the data are 10 years of hourly data from Spain. And again, the key thing is that we have measures of these detailed services that need to function even when we have wind and solar. And that will be kind of our contribution in the bigger scheme of the literature. The approach is very simple. We should regress an outcome of interest on the amount of wind. And here to look at whether things get bad when there is a lot of wind, we separated it into 5 quintile winds. And we look at, are days with the highest quintile wind worse or better than days with the lowest quintile wind? I'll show you that in a picture. For all of these, we will quantify the marginal impact of increasing 1 gigawatt hour of wind, how that affects costs. So for the overall regression, we find that putting 1 gigawatt hour of wind into the grid makes the operational cost, the reliability cost, congestion cost go up. So indeed, wind is making things more complicated, but the number is not very large. It's about 0.2 euros per megawatt hour in a period in which the cost of electricity was about 40 euros per megawatt hour. So it's a very small amount. We also look at whether this is getting worse as we have more and more wind. And what we find is that the marginal effect is not getting worse. Certainly, if we have almost no wind, operational costs go up, but very little. And depending on the specification, we might even say it's close to zero. As we have some more wind, we see that wind is making operational costs go up. But as we have lots of wind, what we find is that it's not getting worse. The marginal impact indeed even might go down a little bit. The reason is that you throw all of this wind in the market, and yes, the market is a bit harder to operate, but also all this wind is putting a lot of competitive pressure in the market, so it's reducing prices even for these additional services. So overall, this is, we thought, an important contribution of the paper because people were worried that this cost would go up very, very high when there is a lot of wind, and we have no evidence to support that. We separated into different costs. This is a bit technical, but we also then look at other outcomes. And what we find is that wind increases these additional costs a little bit, but massively what it does, it decreases cost for consumers. So I was showing you that the marginal increase in cost is about 0.2. I told you 0.2 euros. The prices, the general prices for consumers went down by 2 euros. So it's an order of magnitude higher, the savings to consumers compared to these additional costs that they are creating in the market. We then do a cost-benefit analysis, and the bottom line of this is that consumers were better off, even though this was an early policy in wind, and therefore the subsidies were quite high. So even though consumers paid the subsidies, they still had net consumption benefits. The red dots show you what happens if we ignore intermittency. And if we ignore these operational challenges, we would conclude it was even better for consumers. But the overall takeaway is that the consumer surplus goes up. And ignoring or not ignoring intermittency doesn't change the picture too much. At the end of the day, this was a consumer enhancing policy. For the overall welfare, it depends on how much you want to protect the environment, because here there are some people who are not happy. These would be the traditional producers. So depending on how much value you attach to the cost of carbon, and depending what assumptions you make about how costly wind power is, you can conclude that the policy was welfare enhancing or not. To give you an example, at an $80 carbon tax, which is what we see today in the European market, what we would see is that this policy is welfare enhancing as long as the cost of wind is around 70 euros per megawatt hour, which is on the upper end today on what wind would cost. So overall, this is kind of a positive evaluation of wind, in spite of the challenges that we document in this paper. So the other paper that I wanted to talk about is doing a structural model to understand how transmission benefited consumers in Chile. We will also find net positive benefits from this transmission expansion project. The reason we build a structural model is that we want to understand what happens when you expand the transmission grid. There are other papers that have used regressions to look at transmission impacts, but they look at short-run effects. So as you add more transmission, how do operations change in the short run? Our goal in this project was to also understand how transmission is enabling more and more solar power to come into the grid. Chile is a very important case for this challenge because all of the best solar power in the world is in the Atacama Desert. And this Atacama Desert is very far away from the demand centers in Chile. So building transmission not only allows to put more renewable power in the grid, it allows you to build it in the first place. Without this transmission, you couldn't even build it. So we studied two big ambitious grid projects that basically the main goal was to connect the Atacama region with the north, where there are a lot of mining firms, and then with the south, which is where the biggest demand centers are. So we look at kind of an event study, and we do find that indeed, as these parts of the country are connected, prices become more similar. So I will not have time to go into detail with this, but these very clashing numbers, it's basically very cheap prices in the desert and very expensive prices in Santiago. As the grid expands, we see more similar prices throughout the country. What the paper will do is quantify the gains from trade from this improved expansion, as well as the investment effects from this improved expansion. How much did connecting Atacama with the mining region and the south allow for solar power to blossom in Chile? For those of you, most of you might not know, but solar power has been a boon to the Chilean economy because they had a very expensive power traditionally, and now they have 30% of solar generation that's very cheap there. So I will go a bit quick. In the paper, we also do a regression. This would be the more short-run effects of the transmission line. So as you turn it on, how much does it decrease costs? And we do find that it decreases costs in the market. This is almost mechanical because we are connecting markets better. So costs should go down almost mechanically. In this regression, we find that they go down by about 3 euros per megawatt hour in a period in which prices were around 35. So it's basically a 5 to 10% reduction in costs thanks to this transmission grid. to look at the investment effects, basically how this transmission here and this transmission here over time enabled all these red line. This is solar power coming in. So we do a structural model to quantify how much of this solar power came online thanks to these lines. To build a structural model, and again, I will not have too much time to go in detail, what we have to do is build a production model so that we can see how the grid is allowing for solar to flow better and how it's impacting prices. And then also an investment model where we see how the more transmission you put in the line, the more solar power gets built. So to do the production model, we basically model Chile in different regions, and then we model the power plants in each of the regions, and we also model how they are connected. We have detailed data on how much electricity demand there is in every region, which power plants are in each region, and then we model the transmission line between the regions. So traditionally, the north was completely separate. So we will run the model where this region is completely separate, and then we will see what happens to the model when the region is connected with the rest. So in this hourly model, again, not a lot of time to go over it, but basically it's a cost minimization problem where we try to produce electricity in the best way, given all the different constraints that we have in the system. So we will have power plants sitting in different areas, but importantly, we will also have some limits in trade. These trade limits are given by the transmission lines. We will also have demand in each region that we will have to satisfy. And then we will try to just, again, minimize cost given how much solar power there is, the capacity of every plant, and so on and so forth. For the investment model, it's a much simpler model in the sense that it's a decision of how many solar plants to install. And the way we do it in the paper is very parsimonious. We just look for the zero profit condition. K is the amount of solar power, and we look at how much solar power can you throw into the grid such that they just make zero profits. And this is what this condition is telling you. So the way you solve this is that you solve this, and then you check prices, the profit that the solar farms are making, and you see whether they are making zero profits or not. If they are making still positive profits, you throw some more solar and you run the model again, and you see if they are making zero profits. And this way you can find an equilibrium. So there are quite a few steps in building the model. The data and code are available online if you're interested at the publication website. Once we have the model and the investment model, what we will do is run this thing with transmission line and without transmission line so that we can check how much solar goes in with and without transmission lines. And then we do the full cost benefit. The cost benefit will include the cost of the line, which was 1.8 billion, and then the benefits. The changes in consumer surplus, the changes in solar revenue, environmental externalities, and so on and so forth, as well as the investment. So what we find overall is also a positive story. This transmission line benefited consumers. The way we quantify the benefits of consumers is how many years does it take to pay for the cost of the line. If we ignore the investment effects of the line, this is a bit of a higher number, about 15 to 25 years, even 30 years, depending on the simulation, to pay for the line. You could still kind of justify it because transmission lines take a long time. They last forever. But for a government, it might be a much harder thing to push. However, if we take into account that it allowed for all this extra investment, then the lines pay very quickly, and they pay in about 7 years or 8 years, not very sensitive to the discount rate because it just gets paid very, very quickly. So this is where I had these two cost-benefit analyses. In one case, the cost-benefit analysis is using regression model. In the other case, because we want to look at investment effects, it's looking at a structural model. But at the end of the day, a cost-benefit of these two different technologies, wind and solar, in Spain and Chile. These are two success stories, and we have several others, many more. Really, renewables are working quite well, but obviously there are still some more challenges to be kind of sorted out. In the case of intermittency, here I showed you a period where Spain had quite a lot of renewables, maybe 30%. But now we're seeing markets, Spain itself, that has 60%, 70% of renewables. So maybe we need to revisit the results as we have more and more wind and solar. And for transmission, the Chilean case is very successful because they managed to build a line. But unfortunately, the political economy of building lines is very hard. So in most other markets, what we're seeing is that there are still many bottlenecks to deploying transmission. Even though the expected benefits tend to be quite large, we just don't see these transmission lines happening. So this is, again, two areas of research that are active. And batteries is the third one that I still had no, I didn't have time to share to present a paper, but it would be another one that's making both intermittency and transmission easier. So that's it. Now I think we'll open it to questions.
Thanks a lot, John. Thanks a lot, Mara. So people can now jump in and ask questions for the next quarter hour or so. So please raise your hand or just unmic.
We have two hands raised, but to kick off, there were a few questions in the chat, particularly about the barriers to innovation and adoption of renewable energy. So everything from renewable energy technologies like solar to CCS. Some of the ones that were listed were the high cost of R&D, the high cost of policy monitoring in developing countries. I was just wondering if John and Mara, you could speak to that.
Sure. I've been trying to answer some of the great questions in the chat, and this kind of question came up a lot. So, you know, in general, some of the barriers to the diffusion of innovation, Mark talked about a bunch of them, but you know, there's the question, obviously, of price that matters incredibly, and that's influenced by, you know, government policy. Often there's barriers of information that people often don't know about the cost and benefits of the new technology, and that may also have a role for governments helping out with people's information. There's often skills like, you know, installation of solar panels on people's roofs or heat pumps is often difficult just because you don't have the engineers to help. So all those kind of factors often play in. There is a distinction, I think, between richer and poorer countries. So I think for the pushing the technology frontier forward, like with research and development, a lot of that is often done by wealthier countries. So the barriers in developing countries are often on the diffusion side, you know, those first type of things. But I will say that, you know, one of the things that we found looking at China is that although China started off, you know, in, say, take solar, doing the very low end, very cheap, relatively straightforward production of solar panels, and then gradually over time, or quite quickly in China's case, moved up the value chain, producing more and more sophisticated products, spending more on R&D, and then, you know, now they really are innovating at the frontier. So that movement up the value chain is something which goes a lot with development, and that's one dynamic to think about in terms of the transition.
Yeah, I agree very much with John. So on the technology transfer, how to transfer this technology effectively. For example, one worry with solar panels is that if you put a tiny solar panel, yes, it will make your life easier, but it will not be life transforming. Whereas community solar in Africa, I think could be in many places in rural Africa, could be life transforming. But if you don't have the know-how, you don't have the technology transfer, you could install something tiny and they tell you solar is revolutionary and you have this tiny panel that will charge your phone and you're like, okay, this is very convenient, but I wouldn't call it revolutionary. So I think some transformations can be revolutionary, but without a bit of technology transfer and know-how, I think my worry is only that we might end up seeing things that work kind of, but that could work way better if there is good technology transfer and good kind of joint projects. I would love to see more of that. Yes.
Brilliant, thank you. We'll go now to our live panelists, Jun Gao and Tafreen. Do you guys both want to ask your questions?
Can I go first?
Please.
Thanks. Thanks for both instructors. I'm June, a second-year PhD student in public policy at Harvard, and I have one question for Professor Van Reenen, linking what Professor Reguant has talked about, the intermittency problem. So, do you feel there is a room to study the impact of substitutability between clean and dirty energies due to all those kind of problems Professor Reguant has talked about? And also to Professor Reguant, I wonder, do you feel the what's your I feel this kind of structural models in the field of electricity is very complicated and non-convex and usually not very tractable. Do you feel that has some limitation on what you can do? And so I'm very interested in very general equivalent effect, probably with some insights from trade literature. Do you feel electricity is a good place to apply those more tractable quantitative models or not, due to the complex physics? Thanks.
Thanks, Judd. That's a really great question, and I think the substitutability point, it turns out, is really important around these macro models. So, to get the direct technical change things, for example, that we're talking about, substitutability is important. And if you have relatively little substitutability, then it's often hard to get these things going, and it gives you quite different implications. So I think having a better knowledge of what the degree of substitutability is really important as a good area. It's a complex area, though, of course, because what's happened, it might be very little substitutability in the short run, but a lot more in the longer run. And these things change over time as the technologies change. And it may look, think about the stuff that Mara and I were talking about with solar. If you're thinking about a new power plant, for a long time, solar is very unattractive. And then suddenly the price falls to such a level, it becomes competitive with kind of fossil fuel power stations like coal. And that could be a very almost discrete thing. It's like, do you go one way or the other? When the price gets to a certain level, suddenly it becomes something which is very attractive, and substitutability becomes a much larger thing. So I think that it is super important, and we can use many of the techniques that we already use in other parts of economics, but it has to be done, very, very, very thoughtfully. And as I'll let Mar talk about intermittency, but I think batteries are super important there, because the degree to which you can store renewable energy makes it a much more effective substitute for other forms of energy relative to just being very intermittent and non-storable.
Yeah, so this I will digress a bit because it reminded me of something that I wanted to highlight related to innovation that I forgot about. So what we are seeing is that the sustainability of wind, solar towards the other energies is, in a sense, improving over time, holding the technology constant. Of course, the technology is also improving, but holding the technology constant, it's improving. And this is what I called more market innovation. So with the same solar panels and the same wind farms in the study, if you're interested in this, in the study about Spain, it's more anecdotal because it's a time series, but we highlight very concrete ways in which the market has been redesigned to incorporate renewables better. So the same problem becomes less of a problem because we are running the market better. So it's not better blades, it's not better panels, but it's innovation also that's also reducing the cost of the technology. So I think that's one point that I forgot to make. On your more quantitative point, electricity models are built by engineers, and engineers hate ill-posed mathematical models. So they are generally not that, they are generally well-behaved programs. So computationally, they are usually have a clear solution, but they do require much more computational power than, let's say, a CES function for like 3 countries. So yes and no. It is a bit more complex, but the models are still manageable. I myself have I can ask them to, I will add it in the slides. so that you can find it. But I have some teaching examples and Python, not Python, Julia Jupyter notebooks, where I show how to build these models. And they can be relatively well behaved, but it will take longer to run. You need to make some simplifications and so on and so forth. Yes. And the full network is very complex and is very nonlinear, but economists never work with a real full network model. We work with a linear representation of the network. That's good enough. Yes.
Thank you so much.
Thank you. Reenen, would you like to ask your question? And then we'll go back to one of the chat.
Thank you. It had been very fantastic lectures, the two lectures. I just want to share one of my experience in Bangladesh. I have been working through with IIST regarding the fossil fuel subsidies, and I had the experience of surveying around 600 households in the southern part of the country. So my job was to just locate some villages where there were both grid electricity, solar power, and still the households are using kerosene, the dirty fuel. So just to mention that in Bangladesh, the technological diffusion from solar, from grid to solar in the northern part of the country was possible because actually grid electricity penetration was not possible at that part. So whenever the government thought that it's not possible that there will be a grid electrification in the northern part of the country, it decided, okay, so this section of the country should be electrified through solar. And that was basically due to the irrigation purpose. That the part was the agricultural productivity is largely dependent on the northern part of this country, which is basically also driven by irrigation, and the power was required at that time. So at that time, I surveyed on those areas, and I asked the household, the poor household, that despite having the grid electricity in your village or solar panel, why are you using kerosene still? So they say that they are saving the money for using the solar panel just for the irrigation purpose, though it was a community-based model, but they were not they could not afford them for using the household. Then we also asked them the questions that if you are giving some extra money just to set up a solar panel in your house, so will you be able to use that, or will you be willing to use that? So the response was that is still better for us to spend the money in other purposes rather than using in a clean energy, because we are used to this kind of energy. So having said all of this, my question is this: there is an innovation in the developed part of the world, and there is a technological diffusions that is transmitted in the developing part of the world, but still the poor is far from the accessibility and also the affordability. So it's all about the mobilization of fund, is all about the fiscal decision of the government, that how to incorporate the poor segment of the society to this kind of clean energy. As you say that in
Sorry, if you could just cut there. Thank you.
Thank you.
So I don't know this case well enough. To me, I think eventually solar will be used for most uses in these communities, at least the way you're describing them. I think sooner or later they will be using it, because I come to this from a climate change point of view. I'm not too worried about their use of kerosene, in the sense that for them locally it would be much better for their health. But it is still such a small part of global emissions of CO2 that if they still feel like their money is worth saving for food or something else, I just wouldn't push too hard on them, in the sense that I do think it has to come subsidized to them. Maybe removing the full subsidies is not possible because they are very poor households, but then you need to make solar even more affordable in a sense. But I do understand that given their budget, they might need to make decisions that we would take differently as households. From a climate point of view, these are very low part of the problem. The problem is us. So I think it would be great for their well-being that eventually solar is made cheaply available to them, because it's a much cleaner source of energy. I think it will become more reliable for them. So I would prioritize it more on the energy poverty focus. For the climate focus, I don't think it's that crucial, but again, I would hope for the energy poverty focus that it would be made eventually eventually what we would like, at least me as a climate economist, is that you don't want kerosene even if it's free, because there's something way better out there. We are far from that at the low end of the income distribution, but the ideal would be that the people don't want kerosene even if it's very cheap, but we are not quite there. Yes. I hope I answered at least some of your question. Yes.
I mean, two points I got from your comment was, one, the point about people taking a long time to, adopt a new thing coming along. And, that's true not just of, clean technologies, that's true of any new thing or any new technology. So I think there's a lot we can learn about ways of trying to diffuse things through communities, which are also about trying to, spread information. So for example, often in villages, there's a kind of key people, key opinion leaders or key influencers. And if you can get them to act, then a lot of other people go along with that. So in terms of thinking about programs to get people to adopt, it's often good to think about that sociological aspect to it, that it's not simply, as you said, about the price or everything else. There is a way of trying to overcome inertia to try and spread information. So I think that's an absolutely correct point. The other thing, you said something about that, solar was being adopted in places where the grid wasn't available. And that really reminds me of the mobile phone story. So if you think about the spread of mobile phones in Africa, it was often in places where, for whatever reason, the kind of fixed line transmission networks weren't there. But many communities could just leap to mobile phones because you could transmit things through masts without having all the grid infrastructure. So it became a way of, leapfrogging of certain developments, bottleneck, which is kind of interesting.
Thank you. There were a number of questions in the chat on the cost of recycling for renewables, also on decommissioning. I know this is something that comes up a lot, and if you want to compare it to those costs of fossil fuels as well, please do. But just maybe one last question here to wrap up.
Yeah, so maybe I can take a stab at this. So first of all, I would say that there is an interest of making it sound like renewables are not good for the environment. Nothing we do as humans is good for the environment, but they are definitely way better than fossil fuels. So that's kind of, you will see lots of news about the impact of mining, the impact of recycling. I'm not underestimating those impacts, but I think there is an interest that they sound very bad. And sometimes you will see news that are with that emphasis in mind. Recycling is just starting because most solar panels are still good. But at least the reports that we are seeing is that people expect to recycle quite a bit of it. My expectation is that there will be a flourishing industry that will focus on recycling. I was just reading the other day of a bike company that out of one blade of a windmill made 100 bikes. So that's kind of a cute project that they made 100 bikes out of a wind blade, but if they made 100 bikes, they can virtually make anything that's analogous to a bike that's using a material. So my sense is that we will see a lot of technological innovation in recycling and that it will be quite efficient. We might not be there, but my sense is that at least for solar panels, maybe 85% of the materials can be recycled already. And if we keep pushing that frontier, we might recycle quite a bit of them. I'm not trying to understate the bad impacts of what potentially could be not dealing with it, but the value in those materials is so high that I would be shocked if you just left them there. So that's kind of my crystal balling kind of guess on where things will go, and with some good evidence already that we are going in that direction. Again, it still has environmental impacts, but almost everything we do has, and I do have quite a bit of hope that we will recycle a lot of it. Not all of it, it's impossible, but quite a bit of it. Yeah.
Yeah, I agree with that. I mean, a related thing is there's often a discussion, rightly, of kind of critical minerals and how, many of these things require minerals, and those minerals are often, only available in certain places, and there's geopolitical problems in extracting them and moving them around. So those are certainly true. But just as Mars said, there's often, the market reacts. So in solar panels, for example, silver is a major factor, the silver paste, which is used to conduct. And I think at some point, 5 or 6 years ago, about 10% of all the world's silver was being used in solar panels. But what happened was that firms, because silver was expensive, firms started innovating, and there's been over the last decade, there's been a big reduction in the amount of silver that you need in solar panels because of innovation to try and reduce the amount of silver being used. So I think that, people there's challenges for sure, but there are usually ways of responding to those. And, almost for sure, renewables are creating less of these type of problems, I think, than conventional fossil fuels.
Brilliant. Thank you so much, everyone. I wish we had more time for more questions, but we'll have to wait until next week when we hear Bart Harkstad talk about the international climate action. So Mar, John, thank you so much. And thank you, Robin, for putting this on.
And thanks everybody else for coming.
Thank you, everyone. Thank you.
Thank you, bye.
Right.